Welcome to this talk on reliability. I'm Johan Rhodin, and I've been developing this together with Malte. Malte is not here right now. He's back home in Sweden. So I'll give a brief introduction to the area, then we'll talk a bit about reliability distribution, a new symbol coming in Mathematica 9, together with a failure distribution. There's a whole slew of importance measures to tell which components are important in a system. So we'll look a bit at that as well. And then we'll look at standby systems. What do you do when you have components that fail and you have a backup component for it? And we'll round off with consecutive systems where you connect a number of systems together, and you have to have a number of systems failing for the complete system to fail. So let's get started here with the introduction to reliability. And reliability is used in a number of fields, safety critical things like aerospace, oil, but it's also used in semiconductor design and nuclear power and so on. There's a number of questions you might want to ask, like what is the probability of a car that I made to survive for 3 years and 100,000 miles, whichever is lowest. And as you know, the car manufacturers, it tends to break down just about that point where your warranty is passed. Now, when I talk about reliability in this context, it's we have a number of systems and you can model this on whichever level you like. But here we'll talk about systems like a car. So for the car to work, you'll need the wheels, you'll need the engine, transmission, 1 out of 2 braking systems, and this needs to work in order for the system to work. So that's our ground premises. And in the reliability distribution that we're introducing, the way to model such a system is connecting these by Boolean expressions. So if you're unfamiliar with this notation for AND, that's basically just the AND. So it's the same thing. And this is basically the OR gate. Now, so that system that you see there is the same as the one I'm introducing here: wheels and engine and transmission, and 1 out of 2 brakes and of the 2 brakes. Now, what the reliability distribution is, well, the other part of it is the data. So you'll need some kind of failure data. How reliable are the components? So one of the most used lifetime distributions for data is the Weibull distribution. A Swedish mathematician named Weibull came up with this during the 50s, but I mean the roots of this is even older. And he looked at some steel from a Swedish defense provider, Bofors, and as it just so happens that this is part of the example data. So here we were looking at the PDF for that failure data for that steel. And what you usually look at is not the PDF. A lot of people are interested in looking at the survival function. So let's just look at one survival function here for a Weibull distribution. And here I'm changing the scale factor, and as I increase the scale factor, the survival for the system goes up. Now, right now I'm just showing the Weibull distribution here, but this works for all continuous univariate distributions in Mathematica, and it works for all continuous univariate distributions with a positive domain, so something that fails starting from time 0 and onward. Now, what the reliability distribution does is to package this up into all this theory. It packages that up into a function. So let's create an object here, R, based out of 3 components. So we'll need the X component to work and 1 out of Y and Z. As you can see here, what I'm doing is calculating the survival function, and of course we have all this implemented symbolically, so you can calculate these guys symbolically. And for plot here, I'm just gonna add some lambdas. The exponential distribution is another common distribution used in reliability, unfortunately. I mean, I say that because it's not reflecting reality in a good way, but from tradition, that's one of the distributions that have been used heavily throughout reliability. Now, let's go back to our car example and feed this into reliability distribution. So I'll use that Boolean expression, and I'll also add different lifetime distributions for each component. And let's calculate a couple of functions here. So the survival functions, CDF, PDF, and the hazard function are, of course, all there and readily available. And we can calculate the mean time to failure, and it just so happens to be 3 years for this car. One of the nice things here is that you can combine all these guys together into bigger reliability distributions. So let's look at an airplane here, where we have some distributions for different parts of the airplane, and we'll construct one engine based on those parts, and construct that as one reliability distribution. We can now go on and do the same thing for the complete engine system. So in this example, the airplane needs both wings, and one engine out of 2 on each wing, and of course the control system. So I bake all these guys together into one big reliability distribution, and then I'll calculate the reliability for that big distribution. And in this way, I can calculate typical things like mean time to failure, or this morbid reliability for a 6-hour flight being 98% there, and as well as conditional probabilities. So the failure distribution is basically turning this around. Instead of looking at reliability, we look at failures. So from tradition, this is something that you model with fault trees. So of course we support modeling with fault trees. A basic system could be failure distribution of x and y. So the system fails if both these components will fail. And as in the reliability distribution, we model this with a Boolean expression, and then the distributions for the lifetimes there. So let's look at an application of failure distribution. This is a model of a diesel generator for a nuclear power plant, and so what you see out here is the different events that can happen, like like a pipe somewhere going haywire, or a nozzle or something displaying a faulty behavior. And these events in turn trigger a bigger event. And when this thing here in the middle, when the central event happens, then you're basically you have one diesel generator down, and hopefully you have more than just this guy. So to input this, you'll enter the corresponding Boolean expression and the distributions to match with the Boolean expression. Now I'll put all this together in one failure distribution, and I'll calculate the properties such as CDF and survival function. And for bigger systems like this, it will take a second or two to evaluate. But you get all those functions up there, and you can calculate such things such as mean time to failure, which turns out to be 10 years. And this is given that you don't have any maintenance. So with maintenance, you can greatly improve your reliability. Now, importance measures. Importance measures is something that is really interesting, because say that you have this system and you have the distributions that match for each component and so on. Then you want to drill down and actually find out which components should I improve, which are important, and so on. So we've added 9 new symbols for this into Mathematica, which all take reliability distribution or failure distribution as an argument. And you can directly work with these guys to find out the importance of different components. So let's look at a simple example of this. The structural importance for a simple network. So we have one X component, a Y component, and a Z component. And so what do you think? Which component is the most important for this system to work? Any guesses? X. I agree. And the structural importance also agrees. So the structural importance only looks at the structure. If you want to do more elaborate things, you can use things such as the Barlow-Projan importance here. So the Barlow-Projan importance calculates what's the probability of each component failure coinciding with system failure. So for this airplane example here, or the cockpit of an airplane, this antenna seems to be a good candidate for you to improve on if you want to improve the complete system reliability. So which component would give the highest increase in reliability? Well, then you can use the Birnbaum importance. It's another one of the more commonly used importance measures in reliability. Okay, in standby you have a system which will use one component at the start, and then you'll have a switch, switching in other components as you go. Now this switch can be perfect, or it can also have some failure rate associated with it. So we support that, and you can also have different distributions for the components in standby. So a component that is in standby could be just a perfect component, nothing happens to it, or it could degrade, it could just get worse with time. So this is what it's called: cold standby, warm standby, and mixed standby. Now let's look at an example here of a cold standby system with a perfect switch. Actually, I'll skip this, and we'll move on to a more exciting example of a computer server. So here we have a computer server with redundancy. So you have some redundancy built into the system for hard drives, for network and routers. So this is really what I would call a good server system. And let's compare this with a system, a typical computer system without any redundancy. And we'll see here that the expected time to failure varies from 1.5 years for the simple consumer computer to 3 years for a more server-grade computer. And if we just look at the survival functions there, we'll see how much more reliable the server computer is. So consecutive systems is when a number of consecutive components needs to fail in order for the system to fail. And for this, we've introduced a new symbol in Mathematica called Boolean consecutive function. So it's a new Boolean function, and I'll give you a super brief look at it. So it stays, but if you want to really look at the expression, you can convert it and expand it out to the equivalent Boolean expression. And you'll model this the same way as you do for other Boolean expressions. So you have a structure, and then you have the failure rates for components, and then you can just bake that into a failure distribution or reliability distribution. Now, in this example here, we're constructing a grid of cameras to monitor some system or a room or such. And we arranged this in a grid, a 4x4 grid, and this system has a redundancy, so you can cover all areas are covered until a 2x2 grid in this 4x4 grid fails. Now let's look at reliability for that kind of system, and compare it to a system where you just have 4 cameras and no overlap. So as you can see here, the consecutive system is much better. But you know, when you're constructing that big system, you're using a lot more cameras. So an interesting question is, so what will happen if we use those redundant cameras in standby? All right. So what we'll see here is that it will depend on the mission time for the system, which will be the better system. This takes a second to evaluate, but here you can see the blue one here is for the consecutive system, and the red one is for the camera system with standby cameras. Okay, that concludes the presentation, and depending on who's next, we'll have a few minutes for questions.